welcome back to Organic Chemistry. Today we're going to think a bit more about these mirror image molecules and how they can be drawn in various ways. Now that we know that they're important, now that we know that they're important for biology and they're important for synthesis, because we can control to a certain extent which one we get. If you look on my YouTube channel, which this is on, you can see I put some links under Organic Chemistry to Professor Dave, who explains the same subject in a slightly different way, in more detail. He's quite detailed in his approach. And there's another person, Leo for Science, Leo for Sci, MCAT, who also has a lot of videos on the same subject. I've also linked a few of those. I find her a little bit annoying because she's very slow and very American, but you might prefer the way that she approaches it. It's up to you. It does contain the correct information, and she does explain it very slowly and clearly. So let's have a look at this molecule. Whoops, this molecule here. Yeah, okay, that's good. It's looking good. That's the molecule up on the board there. So you can see there's a chlorine on the first two carbon atoms. That's the green one here. And there's an OH on this carbon atom, and this one is a CH3. So I've drawn it up there with the carbon with the OH and the Cl on the left, because those are the highest priority. That's the one with the most groups on it, so that's going to be our carbon 1. Second carbon has got chlorine on. The third carbon has got nothing apart from hydrogen on it. So we can see it's a methyl ethyl propyl group, so it's some kind of propyl, and it's a propyl alcohol, and it's got two chlorines on it, so it's a 1,2-dichloropropanyl. If we also look at it closer, we can see that this, that I've drawn with wiggly lines up here on the top to show that I'm not decided whether they're up or down yet. And the bottom diagram without the hydrogens on is the actual form that I've got in my hand, which has got, if I put it back to that state for you, hang on, try and get it the same way around, that way. If I put it to the same state for you with this methyl group pointing down, this oxygen pointing down, you can see that the chlorine is pointing towards you, and this chlorine is pointing away from you. This hydrogen is closer to you. Okay, that's better. Which makes it this isomer. It's got two chiral centers. Now we need to draw it, and now we need to also identify them. Let's start with Newman, although it's the second one that I've drawn on there, because it is somewhat easier. The Newman projection is looking from the end. We will use this end. It's imagining that we're looking at the carbon from this end. This is a methyl group, so I'll hold it by the methyl group. Look, try and get it orientated. We will put the OH group upwards. Why not? Put it towards you. So we've got OH upwards there. It's really difficult to organize it because it's backwards to me. Got the OH group upwards. We've got a hydrogen coming towards you and a chlorine coming towards you, and then going away from you is this chlorine, this hydrogen, and this methyl group in my hand. What we can see from this particular type of drawing it is that because this bond can rotate, we can show the difference between this form, which is just a rotamer. So it's a rotated form. There's nothing stopping it going from this configuration to this configuration. But you can see that this methyl group here in my hand is going to interact with this chlorine. Chlorine is a lot bigger in reality compared to the length of the bond than this model shows, and it gets in the way. So it is unlikely to sit like that in the eclipse configuration. It's much more likely to sit at half, where the bonds are half rotated. That's a lower energy. As you can see, as it rotates, it goes high energy, low energy, high energy, low energy. And some, depending on how complicated the molecule, some of these high energies, like this one where the methyl group is pointing towards the chlorine, are higher than others. And in the most extreme state, so if I force the molecule to do something it wouldn't do in reality you can see that in my model I can actually get these two hydrogens to hit each other. Obviously they're not going to hit each other in reality, they're repelling each other by their electron clouds, so that will be a thing that doesn't happen. It doesn't go through that configuration. However, the hydrogen can point in this direction, so it doesn't have to, it doesn't stop it from rotating completely. Depending on the molecule, however, if we have enough things on one side, it can prevent it from rotating unless we heat it up a lot. So now we need to draw it. So let's draw our configuration. I'm going to stand up and do that. So I've drawn the first face, that's over there. That will be where this atom of carbon here on its own, and pointing back from it is the next one, which is this one here, which could be doing something else. You can see that the three lines go to the center, and that's to show that the bonds go to the atom. The second atom is hiding behind, and therefore their bonds will be drawn as if they don't go to the center, as if they're hidden by the circle. This is supposed to represent the carbon atom on the front that is covering up the one behind, because we're looking at it from really close up. So that is my finished drawing of this molecule. It's got these three groups on the front coming towards us like that, and the three groups on the back that have stubby little arms that don't go to the center are the three groups on this other carbon here. That actually, in the case of this molecule, defines the whole molecule, so we don't need to say anything else. It tells us the chirality of both of the centers, which I forgot to mention. Both of these carbons, 1 and 2, have 4 different things on. This has a chlorine, a methyl, and this thing, the ethoxy group. This one has a chlorine, a methyl chloride, so this ethyl chloride, and this hydroxy group on it, so they're both got 4 different substituents on, so they both are chiral, so we can have 2 different centers. We've got 4 different possibilities for this molecule. If we look here, we could have them both pointing towards us, the chlorines both pointing away, or one up, one down in either direction. That brings us to the other possibility, the Fischer projection, which is a different way of looking at the molecule. That is a way where we take the bond that we want to start with. Typically we take one with a CH3 on it. Take the bond that we want to start with, and we put the bond so that we rotate it into a position where it's actually unhappy, where the bonds are actually eclipsing, where they're on top of each other. And we have the backbone of the molecule curving away from us. So this is curving away from you, or curving away from me. The backbone of the molecule is curving away from us. Let me turn it sideways. So we're looking from this angle, and we're looking at this bond here. And we've got these 2 groups pointing towards us and these 2 groups pointing towards us. When we go to the next carbon, we shift it down, so it's not a real case, it's just a way we're reorganizing the molecule to draw it. So the Newman projection is a snapshot in time as it's rotating. The Fischer projection, we've forced it into an unnatural position to draw it in our mind, effectively. So this is the unnatural position with all of the bonds. Whoops, this is the unnatural position, and we're looking at it like that as we progress through the carbons along the molecule. We're going to start again. We'll put this one at the top, seeing as we've done that before, so we'll put this one with the hydroxide group at the top, but we should put a hydrogen behind. So we'll take it like that. It's not always the way that it's drawn. It's a projection that is normally used for sugars, and there's a convention of which of the sugar atoms that you put on the top. It's the one that's most oxidized. In this case, we'll put the hydroxy group on the top because we've started at that end. That's one position, but that is not necessarily the way that they'll always be done. So we're going to take this one. We're going to have this group on the left, this group on the right, so the chlorine on the left, the hydroxide on the right, the alcohol. Then the next one has the chlorine on the left, the hydrogen on the right, and the last one is a methyl group which points down. So it's drawn like this, like a little skeleton. You may recognize these from drawings of carbohydrate molecules like sugars in textbooks. That's how they're always drawn. I will now draw the wedges to show you which way up they are. I've got to stand up to do that. That'll take a little while. So because this molecule is quite small, I can actually draw it in this position with a conventional, nice drawing structure, fully sort of visual version. This is a more diagrammatical one. It's like the skeleton of the molecule. It looks like ribs. This is how it really looks. So these two bonds are going back. This one is flat. These two are coming towards us. So we can draw that with 2 carbons that we're interested in. But if we take this and we want to draw this carbon as well, we would draw it flat as well, but we would, let me take my model, but we would imagine that for drawing this one, we hold it flat. For drawing this one, we also hold it flat. So every bond is rotated, the molecule is sort of moved around to draw each bond. So it's not a real drawing of the molecule, it's just a way of presenting the molecule in a unique way so that we can describe it. Let me draw the other carbon on the bottom here. Obviously it's not chiral, so it doesn't matter, but we will draw it anyway. And go back to the real Fischer projection so that it looks nice. So this is a Fischer projection, including the carbon on the bottom, but because it's a methyl group, it usually isn't drawn out fully. And you can see that we stretch the molecule into a position, we bend all of the bonds straight to get it to do it. So as you can see, even if we draw these highly stylized and simplified versions, particularly the Fischer projection, Newman isn't that simplified. This is time consuming. This is less time consuming, but we have to think about which way around it is. This is specific to rotation around the bond, so it's not used so much for this particular purpose. But you can see whichever we use, it's going to take us a long time to draw the molecule. And as Leah said, I think she called Lee, if you have to draw them all day, if that's your job, if you're making these and you're trying to work out which ones you've made, it becomes a headache very quickly. And so we like to refer to them in a different way. We like to have a short form for explaining which we have. So how are we going to assign R and S to this chemical, to these 2 chiral centers? It will have 2 values, one for the first one for the second one. What we need to do is we need to label these atoms on our molecule and give them a priority. So we need to know which one we're going to call number 1, which one we're going to call number 2, which one we're going to call 3, and which one we're going to call 4 on this atom number 1. So I'm going to rub out the 1, 2, and 3 so that we don't get confused with different numbers, and then we will consider it. So now we are interested in this chiral center. So I've ringed what is connected to it, the 4 different groups that are connected to it, and we're interested in organizing them according to some kind of priority, and the easiest way to do that is by the atomic mass of the first atom that we come to. So in this case, they're all different. We've got an oxygen, a hydrogen, a chlorine, and a carbon, so it's not so hard. They are arranged in order, so we will put the chlorine first because it's the heaviest one, the oxygen second because it's the next heavy one, the carbon third, 12, and the hydrogen fourth because that is the lowest mass. If we have carbons, obviously it's quite likely that we will have 2. We'll come to that when we do the second one. So now what we would like to do is rotate the molecule so that number 4, the lowest priority one, is heading away from us. Unfortunately, in our diagram that's not the case, but there's an easy way of fixing that. At least for me there is, because my brain works that way. So what I'm going to do, this is our molecule, is I'm going to rotate it. Oops, let me move it towards you. This is our molecule, like that. Let's put it like that. This is our molecule, and I'm going to rotate it like that. So now it's away from you. This, where are we? Looking backwards is really difficult. This hydrogen is the one that we're interested in having away from you. These three groups are pointing towards you. And what I want to do is label them 1, 2, and 3. So the 1 is the chlorine, the 2 is the oxygen, and the 3 is the carbon. And we want to know whether that is clockwise or anti-clockwise. So in this case, it's going this way around, which is clockwise. Chlorine, oxygen, carbon. If it was going anti-clockwise, it would be the other one. Let me draw that. So let me rotate this drawing in exactly the same way. That will take me a little bit of time. So there we are. I've rotated the drawing in exactly the same way, and we've got our 3 substituents that are pointing towards us, or forcing this one to point away from us, and that means that we've got a clockwise rotation, so we can define what our chiral geometry of that center is. So depending on who you like to memorize or how you want to remember this, the clockwise circle is R, and Leah likes to say because the top of the path goes to the right, it's R. I guess that's an easy way of remembering it. So now I've drawn a different Fischer projection of my molecule. I've rotated it around because I've been fiddling with the molecule, so it's not the same one as before. And we still want to identify the letter, the chiral center on the top. We want to give it a number or a letter, R or S. And I've deliberately made it difficult for us because this hydrogen on the left is coming towards us, because if we remember, these groups are pointing away. We're looking at it like this. So these 2 groups, the vertical ones are pointing away and the horizontal ones are pointing towards us. They're sometimes drawn like a bow tie. It depends how you want to see it. But if we imagine these 2 are pointing towards us, we're going to have to rotate it, or imagine a rotation or something. There are 2 ways of doing this. One way is we can rotate it. So we can effectively take our molecule and rotate it so that the hydrogen is backwards, like that, which means that we have to change our drawing. Or we can assume that because it's forwards, that we will get exactly the wrong answer, and because there are only 2 answers, we just have to flip it once. That is the Professor Dave way of doing it. So first of all, I'm going to change the drawing by rotating this group to get the hydrogen to the back. So the OH is going to be here and the chlorine is going to be, where are we? We're going to rotate this group so that the hydrogen's at the back. So the OH is going to be on the right, the chlorine is going to be on the left. So using that method, you can see 1, 2, 3, our 3 substituents, this bit at the bottom is the 3rd one, are also in a clockwise direction or right at the top. So this is an R. It obviously has to agree with what we just did, otherwise that would be stupid, but that is how you do it on a Fischer projection. The alternative, Professor Dave way, we will do right now. So you can see if we leave it as it was with the hydrogen pointing towards us, our groups now 1, 2, 3 are in an anti-clockwise configuration, so we would expect it to be S, and we have to do a bit of mental gymnastics to say, okay, we know that we're looking at it from the wrong angle, so therefore it is R. I don't like to do that. That's how some people like to do it. What that means is, if we rotate our molecule so that we're looking at it, where are we? If we're looking towards the hydrogen, obviously these 3 groups, 1, 2, and 3, are in a different order than if we have it pointing in the other direction. To me, it's kind of obvious. It depends how your brain works. Some people prefer it one way, some people prefer it another way. Look at the 2 different possibilities and decide which fits your mind better. I would advise you to have a go at some problems. There are several online. If you're not one of our students, you can have some of our exercises if you are one of our students, and we will look at them and see how well you're doing. It's not hard, but conceptually it's easy to get confused. And here we have it in a Newman projection, so we get the same thing. This time I've drawn it with the hydrogen on the end towards us, so I've drawn it like, with this end of the molecule, the one that we're actually interested in, pointing towards us, which really sucks because automatically the hydrogen is pointing nearly directly towards us. All three of these groups are pointing towards us. So if we do that, we take our chlorine, our alcohol, and the center, which is the rest of the group, pointing away from us into the plane, and that gives us an anti-clockwise direction. But because the hydrogen is pointing towards us, we have to flip that. We could draw it the other way. Let me do that. So to reduce clutter, I've not labeled the ones on the front of the molecule because that's not the chiral center that we're interested in. I've rotated these three round to the back, which flips it round. I used my model so that I didn't get it wrong, but effectively if you rotate it round to the back, obviously the left and right switch over. I've rotated it round upside down as well. Sorry about that. But now we can see if we take our 1, our 2 and our 3, we're back to clockwise because our hydrogen is pointing away from us. Clockwise is correct because we're right on the top, so this is the R configuration. It's not the S configuration, which is the anti-clockwise direction. So now we're back to our molecule because we need to identify the state of the other center. So this one is R. The second one is unidentified yet, but this time I've drawn it the way round so that the hydrogen is at the back. It's the same way round that we had before. Whoops, hang on, I've done something wrong there because the hydrogen is coming out. Both of them going down, that can't happen. So we've got our hydrogen pointing away. The chlorine is priority 1, that's okay. The hydrogen is priority 4 because it's the lightest. And now we've got 2 carbons. So we've got a new case where both of the first atoms are the same. So we need to go another atom away. In this case we've got 3 hydrogens on here. So that is going to be lighter than this one, which has a chlorine on it, which is obviously really heavy. There was a weird cut there. That's because I recorded it, but I got this bit wrong, so I have to do it again. It's a function of not being in practice. You'll discover this as well. Being in practice or practicing this is important if you're going to get fast and do it easily. It's not really very hard, but it takes a little bit of repetition to get going. These modeling kits are not very expensive. They're only a couple of euros. You can get them from Amazon or eBay, all kinds of places, from local source. They are worth having. You can also make a model out of food, for example, grapes and cocktail sticks or something. It is nice to have a 3-dimensional model to remember, to start with, to think about this, and then you won't make as many mistakes as I did. So we've got our 1, our 2 and our 3. This is an anti-clockwise one. So that is quite handy actually, because that means this is an S center, this one was an R center, so our first carbon is an R center, the second carbon is an S center, so this would be RS 1,2 dichloro 1-propanol.